Okay, what we're going to do today is what I call a summative overview of Pre-Calculus 1 as it's taught at this institution and in my sections. Um, okay, see that little delay. Yeah. We begin, we began the course with graphs of a few toolkit functions. The main toolkit functions were squaring, exponential, and inverse functions. Squaring function has a graph that looks like this. Exponential function has a graph that looks sort of like this. And when I say inverse, that's really not the word I wanted to use. Apologize for that. This is reciprocal because inverse has a couple of meanings that we don't want to confuse. And the reciprocal function has a graph that we learned to construct that looks like this. The constructions for these graphs, I'll review just very quickly. We start with a square or a rectangle. And so I'll just say, usually I'll say a rectangle because the dimensions of this thing are as you wish them. I put a red dot at the midpoint of the lower edge. I've got center lines, lines that divide the rectangle vertically and horizontally. And then I can do a couple of construction lines halfway between each edge and the center line. And then horizontal lines. Notice that this line is halfway from the top to the bottom. Now I'm going to go halfway from this line to the bottom, halfway from there to the lower edge, and halfway from there to the lower edge. These have been drawn very accurately, but I put a point at the left edge of the rectangle on the lowest dotted line. I call these construction lines. And then on the next construction line, I put another. Well, I move over one construction line and up one construction line, over one, up one, over one, up one, over one, up to the right edge. And there's a graph, and it's a fairly accurate graph of an exponential function. If you draw this carefully, you get a good picture of the exponential function. So I'm not going to label these. You can tell which one's the exponential, which one's going to be the square, and so forth. Squaring function is constructed almost identically. Put a red dot on the lower edge, the center of the lower edge, and we subdivide it just as for the exponential. But then we do one more line halfway between we have the construction line halfway between the right edge and the middle. And then halfway between that construction line and the middle, we draw another one so that these lines are twice as close. The one in the middle is twice as close to the one I just drew, and the one I just drew is also twice as close as, I'm developing a bad sentence here, but as I'm going to abandon that sentence. Okay. This thing is halfway between this one and halfway here. And we can see that some of these lines are twice as close together as others. Okay. Then we, just as with the exponential, we go halfway from the center to the bottom to the lower edge, halfway from there to the lower edge, halfway from there to the lower edge, and then one more halfway from there to the lower edge. And this is a small graph, so that line is almost invisible, but I'm going to continue it out here. So we can see that we have 1, 2, 3, 4, 5 lines, each twice as close to the lower edge as the one before it. We sketch the graph as follows. We start at the upper left-hand corner of our rectangle, move over one construction line and down two. So horizontally over one construction line, down two. And then over one construction line, which takes us to the middle, and down two. The reason I drew that last construction line was so we could go down two from here. In any case, that takes us to the center, to the red dot at the middle of the lower edge. And then we move over one and up two, over one, up two, over one, up two, and we sketch a curve. Reciprocal function. We divide it vertically the same as we did with the squaring function. Horizontally, of course, we divide it in the middle. And in this case, the red dot goes here. Then, halfway from the upper edge to the middle, we sketch a line. Halfway from the lower edge to the middle, we sketch a line. Then halfway from each of those lines to the middle, we sketch another horizontal line. Then we start on the construction line just below the middle line, okay? The construction line right here. You move over one, down one, and over one and down one, giving us this curve. We then start on the construction line just above the middle on the right edge. We make a mark and then left one, up one, left one, up one, and there's a curve. Well, those are constructions. Now, not everybody will have done those constructions. Not everybody is required to do those constructions. But as it turns out, as we found out, if each of these is drawn in a 4x4 rectangle with the red dot at the origin, we then get, this should be y equals 4. Okay, so the rectangle is 4 units by 4 units, -2 to 2, 0 to 4. All right, now we can label these construction lines. If this is y equals 4, this will be y equals 2, y equals 1, y equals 1/2, y equals 1/4. I'm not going to label these because we've done a lot of labeling, and everybody should know what the labels are. In fact, I'm going to go ahead and label y equals 4 here, y equals 0 here. This horizontal line will be y equals 2. This is our y equals 1 line. If I extend this out a little bit, it's our y equals 1/2 line. And then we have the y equals 1/4 and y equals 1/8 that I'm not going to sketch in. Okay. Okay. In this case, this is the graph of y equals f of x equals 2 to the x. And we can easily make a table and confirm this. And this one is y equals x squared. Now let's see the f of x notation. And this is equals f of x equals 1 over x. There are other graphs. We have the reciprocal square and the cubing function. But if we understand how these graphs are constructed, we can actually construct the others. And there are also the power functions we'll talk about in a little bit. But let's look at what these three functions tell us. If I specify an x value on this graph, and I'll specify that okay, so here is some x value. Getting a little crowded here and should have given myself a little more space. There's an x value, and it intersects the graph, the curve here. Then this value will be f of x. The y value at this point will be the value of f of x. If I specify a y value, let's say I've got a y value here, that's going to intersect the graph at a point. And the x value here is the solution to the equation y equals, I don't have room to write this, should have anticipated it and really should be going with a bigger graph, but okay. The solution of y equals f of x. Now let's draw that a little bigger. So that in general, any function we have let's say this is a graph of a function, as we'll see later. That could be the graph of some kind of, or at least a part of the graph, some kind of a polynomial function. So if we have a value of x, then again, the y value at this intersection point is f of x. If we specify a y value, then where the graph intersects the curve of y equals f of x, I'll say the solution of y equals f of x. So the x value here is a solution of f of x equals y. And I'm going to rethink this, and I'm going to label this f of x equals y. So for example, if we had the exponential function, the equation y equals f of x would now be y equals 2 to the x. And we'd have to solve that equation. So an example, for f of x equals 2 to the x, 2 to the x equals y, as we have discovered recently, fairly recently. This transforms to the equation log base 2 of y equals x. So if we know what the value of x is, if we know what the value of y is, so if we know the value of y, we can evaluate log base 2 of y and get the corresponding x value. What we want to look at first is how we can calculate f of x if we're given x, and how we can figure out what x is if we're given y. Squaring function I'm setting up a couple of columns here. The equation f of x equals y. Well, the squaring function f of x equals x squared. Define f of x. We just take our value of x and replace it here in the expression f of x equals x squared, the defining equation for our toolkit squaring function. So we just plug x in and we end up having to square x. So we'll do an example of that in a minute. The equation x squared equals y has a solution x equals plus or minus the square root of y. Okay, so we take the defining relationship. If we're given the value of x, we just plug it in to the defining relationship. If we have the equation f of x equals y, that equation becomes x squared equals y, since f of x equals x squared. Okay. And we solve that equation, and the equation is very easily solved. Okay, to the exponential function, our equation f of x equals y would be 2 to the x equals y. The solution x equals base 2 log of y. To find f of x, now we got f of x equals 2 to the x. Plug in the value of x. The reciprocal function, our f of x equals y function would be 1 over x equals y. Our solution is x equals 1 over y. Our function value is f of x equals 1 over x. Our solution, well, to get the value given x, we plug in the value of x. That's kind of a synopsis of how we'd solve these three types of equations. Now we can transform these functions. Stretch and shifting transformations. Y equals f of x minus h. We shift plus h units horizontally. That means that if we have the graph of 2 to the x, then f of x minus h would shift this graph h units in the horizontal direction. If h is positive, it would shift this way. If h is negative, we shift this way. Now, if it's f of x minus h, then if h is positive, we end up with the minus sign here. If h is negative, then the minus h would give us an x plus something. So we're pretty much used to that, but be careful about that. Okay. If we have y equals f of x plus k, that takes the graph and shifts it k units in the vertical direction. Y equals a f of x. We stretch the graph vertically by factor a. Reflect this. If a is negative, so this is a stretch reflection factor, and it can also compress because if a is less than 0, stretching by factor a actually compresses. I'm sorry, if a is less than 1, stretching by factor a actually compresses. So this compresses if the magnitude of a is less than 1. That's a summary of stretching and shifting transformations. There is one more transformation that appears with the exponential function, and I'll mention it later. Transformation, we do all three. First, and that gives y equals a f of x minus h plus k. And we want to look at these functions. Now, one more detail. Domain and range. Okay, I'm not going to do the domain and range for everything because actually I've got room to list it over here, so I'm going to go ahead and do that. And I just realized that some of what I wrote over here, what you do to find f of x, was off the screen. And there it is. So you can see it all. So okay, we want to do the domain and range of each function. The domain of the function as constructed. And this is for the toolkit function. The domain of the toolkit squaring function goes from -2 to 2, meaning that every x value between -2 here and 2 here has a point above it or below it on the graph. Okay. The range consists of all the y values. So that means for every y value between 0 and 2, the question is there a point on the graph? And there is. For every y value from 0 to 2, if you draw a horizontal line, you're going to meet the graph. So the range is 0 to 4. For the exponential function, again, the domain is from -2 to 2 because there's always a point on the curve above every x value. The range is not 0, 4. Now we've drawn it in a rectangle that goes from y equals 0 to 4. But there's no y value below this one. Okay, remember, this point is on the left edge from the construction line directly above the left edge. And that construction line is the line y equals 1/4. If we subdivide this, you got 4 here, halfway to the lower edge is 2, halfway there is 1, halfway there is 1/2, and halfway from there is 1/4. So the range is 1/4. For the reciprocal function, this is a little trickier. Now, one thing that we don't do with the reciprocal function is we don't try to connect this point to this point. And construction-wise, what's happening here is every time we move twice as close to the center, we move twice as far from the horizontal center line. So here we're twice as far from the horizontal center as here. And then here, we're twice as far from the horizontal as we were here. If we move twice as close to the center line, again, if we were to draw the line here, we would have to move twice as far from the horizontal center line, which would move us to a point about down here. We could keep moving twice as close to this vertical center line. Every time we do, we're going to have to double our distance from the horizontal center line. And pretty soon we're going to be at the center of the earth. Okay? Wouldn't take that long. You could, count that many moves in just a minute. Okay? So you have a vertical asymptote. It's going to form a vertical asymptote, and we're going to form a vertical asymptote here. We also get a horizontal asymptote here and a horizontal asymptote here, as we've seen. Just reviewing the fact. In any case, the domain is -2 to -1/2 as constructed, union 1/2, 2. And you want to review what the domain of the entire reciprocal function is. If you keep extending this graph, you get every y value except 0. And you have a point of the graph for every x value except 0. Okay, so again, you don't connect this line to this line because the graph keeps getting closer and closer to the vertical center line. And that never stops. And it keeps going lower and lower. From this edge, or from the right edge of the rectangle, every time we go twice as close to the vertical center line, we go twice as high. So we're going to have a graph that just kind of blows up in this direction. So it blows up this way to the left of the vertical center line. It blows up this way to the right of the vertical center line. And similarly, we keep going twice as close to the horizontal center line. This point is twice as close as this. This point is twice as close as this to the horizontal center line. So we could move twice as far out again and go twice as close and continue doing that. We keep going twice as close and twice as close. And pretty soon we're very far out and we're still going twice as close. So that we're going to have a horizontal asymptote. And similarly, on this side, we'll have a horizontal asymptote that comes up from below. Okay, so as graphed, in basic rectangles, main and range is the interval from -2 to -2 to -1/2. That's from here to here, and then from 1/2 to 2. Let's look at the k f of x minus h plus k expression for each of these three functions. Now I'm going to list a couple more functions. Include 1 over x squared and x cubed. We've seen how to construct these. I'm not going to do the construction right now. Then we want to get the AF of x minus h plus k expression. I'm going to include a column for f of x minus h. So if we have the x squared graph, we have f of x equals x squared. So f of x minus h, we're replacing x by x minus h. Replace this x by x minus h, and we get f of x minus h equals the quantity x minus h squared. Again, this is exactly the same as this, except that x has been replaced by x minus h. If we have f of x equals 2 to the x, f of x minus h is 2 to the x minus h. The x minus h goes in the same place as the x's in this definition, so that this expression is identical to this expression, except x has been replaced by x minus h. If f of x is 1 over x, then we replace the x's by x minus h. F of x minus h equals 1 over x minus h. F of x equals 1 over x squared. Replace the x's by x minus h. We get f of x minus h is 1 over quantity x minus h squared. If f of x equals x cubed, then it should be clear that f of x minus h equals x minus h cubed. Then a f of x minus h plus k becomes a and k are just what they are. F of x minus h is x minus h squared, so we're going to replace f of x minus h here by x minus h squared. In the case of the exponential function, f of x minus h is replaced by 2 to the x minus h. In the case of the reciprocal function, let's write it. Okay. Actually, I want to write it. In a way that makes it obvious. Common mistakes here are putting the k inside the parentheses with the x minus h. Doesn't go there. You multiply a by whatever f of x minus h is, and then you add k at the end. It's order of operations. Okay? Multiplication, then addition. Well, the other two forms are a times 1 over x minus h squared plus k and A times x minus h quantity cubed plus k. If we construct these in a 4x4 rectangle, well, if we construct these in a rectangle, the rectangle becomes, well, the dimensions of the rectangle become 4a by 4. If the red dot is at the lower center of the lower edge, the coordinates of the red dot VHK. If we've graphed the reciprocal function, then the dimensions of the rectangle are as before. And the red dot is at HK. This would be the graph of A f of x minus h plus k. Be this one or this one. Now, what I want to begin addressing right now is equation. Let's say the equation A, f of x minus h plus k equals c. With the squaring function, it's A times the quantity x minus h squared plus k equals c. For the exponential function, it's A times 2 to the x minus h plus k equals c. For the reciprocal function, A times 1 over x minus h plus k equals c. For the reciprocal square, and if you don't remember these names, you really need to review the toolkit functions because they're kind of the basis for the whole course. It's A times 1 over x minus h squared plus k equals c. And for the cubing function, it's A times the quantity x minus h cubed plus k equals C. I want to talk about how to solve each of these equations. And I'm going to need more room. So let's do that. Equation A times x minus h squared plus k equals C is always solved by first getting rid of the k on this side. Remember, we're trying to isolate x. First, we get rid of the k. I'll just say we subtract k. Implicitly, we're subtracting k from both sides. I don't want to write all that out. I don't think we understand how that works. Whatever the value of k is, whatever the value of c is, we're going to subtract k from both sides. And we're going to get whatever a and h are. A times x minus h squared equals c minus k. Divide by a. So that x minus h squared is whatever number we get when we do c minus k divided by whatever a was. And then x minus h is plus or minus the square root of c minus k over a. Okay, let's see. Divide by a. I'll just say plus or minus square root on both sides, actually. We get this. And we add h to both sides. We get x equals h plus or minus the square root of c minus k divided by a. So for example, of two horizontal shift of minus 3 vertical shift of 5. A would be Okay, I wanted to write what C equals here, but that's not a general thing, so I hesitated. And I'm just simply going to write this out. What we get then is 2 times the quantity x minus -3 squared plus 5 equals whatever number we want to get. So we're going to say maybe 7. I'm going to put a period here. There's our equation. And I can accompany that with a picture, but all I've done is I've written out this form with the values of A, H, and K, and then some arbitrary value of C, which I chose to be 7. What do we do? First thing you want to do is subtract 5 from both sides, right? We get 2 times x plus 3 quantity squared equals 2. If we subtract 5 from both sides. So just like first step here where we subtracted k from both sides, we get c minus k. Well, c is 7, k is 5, so we get 7 minus 5 equals 2. We don't need to memorize this form in order to understand that what we want to do is subtract 5 from both sides. And then divide by 2, and we get x plus 3 squared equals 1. Plus or minus the square root. We get x plus 3 equals plus or minus 1. Then here I say you add h. So I'm going to say add -3 to both sides. We get -3 plus or minus 1. So we get x equals -4 or -2. We could write the solution set -4, -2. Now let's see if -4 and -2 both work. How do we check? We plug -4 into this equation. X is -4, then we have -4 minus -3, which is the same as -4 plus 3, which is 1. We're going to get 1 inside the parentheses. We square that, we get 1. I'm sorry, we're going to get -1, but when we square that, we get 1. Multiply that by 2, we get 2. Add that to 5, we get 7. Now, I didn't do that, but we always want to write out the check. Okay, so there's one way of solving this equation. Now, there is another form of the equation. We could expand this equation and get the ax squared plus bx plus c form, okay, and solve it as a quadratic equation, which I assume everybody is familiar with. Try to work within this scheme just to show how this scheme works. So we've solved this equation. Okay. Problem with the board here. Hang on. Second form, a times 2 to the x minus h plus k equals c. Let's go ahead and use the same vertical stretch and horizontal shift that we did before. So using the same values of a, h, k, and even this arbitrary number c, we get 2 times 2 to the x minus negative 3 plus 5 equals 7. Well, first we're going to write that as 2 multiplied by 2 to the x plus 3 plus 5 equals 7. Then we're going to subtract 5. We're going to get 2 times 2 to the x plus 3 equals 2. Divide both sides by 2. We've got too many 2's here. I'm not writing out the steps because they're the same as before. But let's go ahead. Subtract 5. Well, I'm going to write out simplify here. We simplify by doing the negative with negative 3 and getting the plus 3. Then we subtract 5 on both sides. And that's going to get rid of the 5 and give us a 2 over here. Divide by the 2 out in front, we get 2 to the x plus 1 equals 1. We change this to log form. Now that really isn't necessary in this case. We know that 2 to the 0 equals 1, so x plus 1 has to equal 0, but we're not going to use that, okay? We're going to say x plus 1 equals log base 2 of 1. X plus 1 is the log of 1 over the log of 2. In this case, we get x plus 1 equals 0. We plug this into the calculator. Now, if the number here wasn't 7, if the number here was 12, or let's say the number here was 9, now 10. Let's say the number here was 10. When we subtract 5, we get a 3 here instead of a 1. Now we know what the log base 2 of 1 is. We know it's 0. We know the log of 1 is 0 for any log function. But if we had a 3 here, then we'd have log base 2 of 3. And the solution would be log of 3 over log of 2. And you'd have to plug that into your calculator. Okay. But once we get it down to here, if you just know the rules for logs, you get it easily. We find that x equals negative 1. And that process would work for any exponential function. For the reciprocal function, we get using the same A, H, and K as we did before, and the same value of C. The reciprocal function, the AF of x minus h squared, or AF of x minus h plus K form is this. So plugging in values of A, 2, A, that's H, and C, the equation becomes this. Now we rearrange multiplying 2 by 1 over x minus negative 3, we get 2 over x plus 3. It's like 2 over 1 times 1 over this. And minus 3 is plus 3. Okay. Now we subtract 5, we get 2 over x plus 3 equals 2. At this stage, we want to multiply by our denominator. If we have denominators in an equation, we want to clear them by multiplying by at least common denominator, or at least some common denominator. Least common denominator is better because it's less work. But in this case, we only have one denominator, so we don't have to worry about that. So we're going to do x plus 3 times 2 over x plus 3 equals x plus 3 times 2. Now, in this case, we're multiplying a fraction by x plus 3, so it's prudent to write it as x plus 3 over 1, so we can literally use the rule for multiplying fractions. If we multiply the numerators, we get 2 times x plus 3. We get denominator x plus 3. X plus 3 is a factor of the denominator, and it's a factor of the numerator, so we can divide this x plus 3 into this x plus 3, which just gives us 1. On this side, we multiply through by 2, we get 2x plus 3. Once we divide this out, we get 2 equals 2x plus 3. And we solve for x, which is straightforward in this case. So what we've done is we've multiplied by the denominator. We simplify again. Simplify by dividing the x plus 3 into the x plus 3. Then we solve this for x, which would mean we're going to subtract 3 from both sides. We're going to get 2x equals negative 1. And that's very straightforward. We get x equals negative 1/2. Something about that. And check this. I get 1 over x plus 3, which is going to be 1 over 2.5. And 1/2 is same thing as 2/5, 4/5. Somehow I'm not getting 2 out of that. Did I do something wrong? Be a lot of fun to catch me. Okay. Um, just check my steps because something doesn't feel right. Yep, I knew something was wrong. It didn't check. When I plugged -1/2 in here, I was getting fractions, and I can't get fractions. Well, I was careless. When I did x plus 3 times 2, I did something I commonly see students do. I multiplied the x by 2, but I didn't multiply the 3 by 2. That should have been 6. So we're going to get x equals -2, which is pretty obviously the solution. If x is -2, then x minus -3 is x plus 3, which would be 1. So then we have 2 times 1/1 plus 5 equals 7. And you can write that out and work it out. You just get 2 plus 5 equals 7. So I'll just say, be sure you check. And I'll say that that one is checked. Okay, well, I'm out of board space here. I should go ahead and complete the rest of these solutions. Always here. And my choice is going to be to do the other thing that I really want to do, which is draw pictures. Okay, this equation without drawing all the construction lines. Just going to say that the graph looks something very much like this, where this dimension here is 4a. This dimension here is 4. And the red dot, which I run a little closer to the middle, is at hk equals -3, 5. If hk equals -3, 5, and this is the line where y equals 5, 4a, remember that a was 2. Okay. So that means we've taken our 4 by 4 rectangle that we started with, and we got to multiply every y value by 2. Now our 4 by 4 rectangle for the squaring function goes from y equals 0 to y equals 4. So when you multiply all the y's by 2, we go from 0 to 8. So 4a, let's just write out what a are, a, h, and k are. Okay, 4a is 4 times 2 is 8. So this is the line y equals 5. This is going to be the line y equals 5 plus 8. That's a line y equals 13. Okay. Now, as we've done, we can subdivide, we can do all the subdivisions and everything and label a complete scale. But we're trying to solve for c equals 7. And c is what the value of y should be for this graph, or the value of y that we want to look at for this graph. Okay, well, c equals 7 turns out to be this green line. That's y equals 7. The green line intersects the graph at this point where x equals what? Well, if the width of the graph is 4 and x equals -3 at the center, so let's just go ahead and label x equals 3 here. If the width is 4, then half the width is 2. So this distance would be 2. So x would be 3 plus 2, or 5. And in this edge, x would be 3 minus 2, or 1. So x is 1 here, x is 5 here. And I'm wrong. It should be -3, because h is -3, right? Okay, this is a line where x is -3. I just carelessly wrote down 3. So if we go 2 to the right of -3, we get -1. If we go 2 to the left of -3, we get -5. Here's a point where the y equals 7 line intersects the graph. We estimate the value of x at this point. And then we have another point where we intersect the graph. That would be here. And we estimate the value of x here. Well, this vertical line looks like it's halfway between the left edge and the middle. Left edge is at -5, the middle is at -3. So that would be -4. This point looks like it's a little closer to the right edge than it is to the middle. So our estimate might be x equals -1.8. So we compare the solution set. Which is -4 negative 1.8. With the solution of our equation. It says equation, I muffed that Q. The solution set of the equation was -4, -2. So which do we believe? Well, if our estimated solution set is far from our solution set, then we'd better go back and make sure we did our construction correctly here and make sure we did our steps correctly here. Whichever one we're more suspicious of, we check it out. We need to reconcile the picture with our algebra. And then we would do the same for the other equations. Of course, we're out of time now, so we'll continue this in our next class, which will be a week from today, because we have a Thanksgiving break. Okay? So have a great break. And hopefully that gives you a little bit of the big picture that we're trying to develop in this course.